Okay, in Online Excel Lab 9, we're going to look at hypothesis testing. Specifically, we're going to look at 4 very common hypothesis tests that you might do as a statistician working for various manufacturing companies. Before we do that, we want to download the template, which I've already done here. Question 1, your company owns several cocoa bean farms. You want to distribute your cocoa beans in the US, but you are informed there are FDA standards that your product must meet. You read the FDA's Food Defect Levels Handbook to learn more about this process. I've already opened it up right here. You learn that you need to test for mold, insect filth, and what? So I'm going to copy cocoa beans here. I'm going to paste it right there and hit down. And I see that this first column is the product that we want to import. The second column is the defect. And the third column is the action level. Action will be taken against your company if you don't satisfy the standard listed below this in this action level column. So mold, insect filth, and mammalian excreta. I'm going to copy mammalian excreta and paste it right here. The first two food defects you've already tested. We're going to assume that you already tested for mold and you already inspected for insect filth. The last thing you have to inspect for is mammalian excreta. Now, you've never heard of it, this third food defect, so you decide to Google that, right? So I'm going to Google mammalian excreta. And I come across this article, and I do. 9 disgusting things that the FDA allows in your food. So let's find mammalian excreta. Okay, so according to this article, mammalian excreta is a rather polite way for the FDA to tell you that there's rodent poop in your food. The FDA allows a certain level of rodent poop in your food. Now I copied it in, but I made sure there's no space before and after the phrase rodent poop. Now your company will trigger an FDA action if you're submitted cocoa bean samples average 10 milligrams or more of a mammalian excreta per pound. So 10 milligrams or more of mammalian excreta per pound. Now, because this standard is an average of 10 milligrams or more, it includes the word equal. So if it equals 10 or exceeds 10, then it's going to trigger an FDA action against your company. That statement would be the null hypothesis. And so down here, our null hypothesis, HO, is mu greater or equal to 10, right? That's an average of 10 milligrams or more mammalian excreta per pound. The alternative hypothesis is the opposite of that. So an average greater than or equal to 10 would be an average less than 10. So this is a one-tailed test, specifically the lower-tailed test, because we're pointing to the lower tail of a normal distribution or t-distribution, right? Now the data is at the bottom of this problem. So I'm going to copy this data into my template. Okay, I'm going to copy it right over here. I'm going to paste and match destination formatting. So I right-clicked or I two-finger click the mouse and I get this. I'm going to match destination formatting. And then I'll widen this up. Now I'm going to name this set of numbers. I'm going to go to the bottom here. I'm going to delete the S from submit question. I'm going to name all these numbers, the set of numbers. I'm going to name it defect. Okay, so everything in this highlighted box, everything in this highlighted box is the object defect, right? So let me go back up here. This is the hypothesized value 10. Okay, so this is the hypothesized value 10. I'm going to do a count A function, and then I'm going to type defect. And notice when I type defect in parentheses, the numbers are highlighted in a blue box. So I know that I've named it correctly. And I get 50. So there are 50 beans in my sample, right? 51 pound randomly selected cocoa beans. 50 these are pounds, right? Now the average is the mean is the average of defect, right? The object name defect. And my average is 10.691. 10.0691. The decimal places should be 40. I mean, 4 decimal places. So these are 4 decimal places. Whoop, sorry, 4 decimal places. The standard deviation of the sample is found using stdev.s because it's a sample. We want the sample standard deviation of defect. The sample standard deviation is 1.4984. The standard, now this is the standard deviation of this set of 50 observations. And your standard deviation is going to be different than my standard deviation. Your mean is going to be different than my mean. So this is the standard deviation of these observations. This is the estimated standard error of the means. The sample means will vary from sample to sample. So if there are 60 people in this class, 60 people are going to have 60 different sample means. 60 different sample means. Those sample means are going to vary. So what we're calculating here is the estimated standard deviation of the sample means, plural, which is also known as the standard error. And that is calculated by taking the, I'm going to type equals, I'm going to put standard deviation of my observations, of my 50 observations in the numerator, and then I'm going to divide that by the square root of the sample size, which is 50, right? In my case, right? So the standard error is the standard deviation of my observations, right? Divided by the square root of my sample size, 50, right? And this will vary amongst us, right? Now the test statistic starts with the point estimate of the difference. Point estimate of the difference is the sample mean, right? We're estimating mu here with the sample mean. So the point estimate of the difference is the sample mean minus the hypothesized mean. That right there is the numerator of the test statistic. Call that the point estimate of the difference. And the probability of it being 0 is 0 because this sample mean can take on infinite many values, whereas this is 10. That's the standard, right? There's only one 10 on the number line. But the sample mean can take on infinite many values on the number line. And so 1 divided by infinity is 0. So the probability that this test statistic is 0 is 0. So there's going to be a difference. The question is this difference here significant, right? So the first step we have to do is we have to divide the point estimate of the difference by the standard error. Okay, so we're dividing the point estimate of the difference by the standard error, right? The sample mean minus the hypothesized mean, or the FDA standard 10, divided by the standard error. and that equals 0.3260. Now, because the standard deviation varies, this is the standard deviation of my sample. Your standard deviation will vary. It'll probably be close to my value, but it's going to be different, right? So we're not using the population standard deviation. We're using the sample standard deviation. And so this is an estimate of the standard error. If we knew the population standard deviation, this would be the standard error. But we don't know the population standard deviation. The sample standard deviation varies from sample to sample. So we have an estimate of the population standard deviation. In that situation, we have to use a t-distribution. And a t-distribution has the degrees of freedom. And the degrees of freedom are equal to the sample size minus 1. My degrees of freedom are 49. Yep. Let's go through and make sure that we got these answers correct. The sample size is 50. My mean is 10.0691. My standard deviation of my sample is 1.4984. My standard error is 0.2119. That's the estimated standard error, not the actual standard error. It's the estimate of it because we don't know the population standard deviation. My test statistic is 0.3260. And my degrees of freedom are 49. Again, 50 minus 1. Right. I'm going to hit enter. And it looks like I got everything correct so far. Now, if you look at the p-value, it tells me to use statdistributions.com to graph and find the p-value of the test statistic. And I want to verify it with t-inverse or t.dist or norm.s inverse or norm.s dist, right? So first I'm going to open up the statdistributions.com website. Okay. My significance level is 5%, right? The significance level is 5%. It is to the critical value of the test as the p-value is the test statistic. So the p-value is the probability of being outside the test statistic. The critical value is the alpha level is the probability of being outside the critical value, right? So these two go together like test statistic and the p-value go together. Okay. So to find the p-value, I got to put in the test statistic into the statdistributions.com problem. Okay, so there's my t-value. And then I got to come up here to my alternative hypothesis. My alternative hypothesis says it's a lower-tailed test. So I want only the left tail of the distribution here. And so I got the left tail of the distribution. I got a p-value of 0.3260. And then I need to set my degrees of freedom. My degrees of freedom are 49. Yep. So my p-value is pretty close to 0.0627, but I need it to 4 decimals, not 3 decimals. So I'm going to put that in here. Right? I'm going to put that in here for right now. Right? My p-value is quite large. Again, this is a lower-tailed test, so the p-value has got to be to the left of my test statistic. That's my test statistic. And my p-value is probably being less than this test statistic, which is the area to the left. This alternative hypothesis is pointing to the left. So we're looking at the left tail, right? So my p-value is quite large, right? So let me use Excel to verify that 0.627 is pretty close to my p-value. So what I'm going to do is I'm going to use equal p, because again, population standard deviation is not known. If I do dist, I need a number on the number line. And the number on the number line is my test statistic. Then I do comma, degrees of freedom. My degrees of freedom are 49. And then in Excel, I need to type true here. If you're using Google Sheets, you don't need to type true. And I get a p-value of, pretty close. The number that statdistributions.com gave me. 0.6, not 0.627, 0.6271, because we need it to 4 decimal places. Okay. Now, before I go on, I want to find the critical value of the test. And the critical value of the test is found by changing the p-value to our significance level of 0.05. 0.05 is 5%. Okay, so this right here is our significance area. This is significance. It's a one-tailed test. It's to the left because it's the lower tail test according to our alternative hypothesis, right? And it produces a critical value of 1.677. Okay. So way this works is this right here is if the test statistic is under the white part of the distribution, I have evidence in support of the null hypothesis, greater than or equal to 0. If the test statistic falls under the blue area is the significance, right? The blue area is the significance. And if it falls under the blue area, since this side of the distribution is negative, we say the difference is both negative and significant. So the test statistic falls under the blue area being the significance level. We say the difference between the mean and the hypothesized value of the mean is negative and significant. But that's not the case in my situation. My test statistic is under the white area, which means I have evidence in support of the null hypothesis. Now, I can't accept the null. What I can do is I can say I do not reject the null. So 5% significance, I cannot reject the null hypothesis. Okay? You can reject the null hypothesis, which means you can accept the alternative, but you cannot accept the null hypothesis. And you have to use language here to avoid making a type 1 error. Now, because I cannot reject the null hypothesis, I cannot say this is false. Basically, what I'm concluding as is that the average is 10 or more. My data is saying the average is 10 or more, right?